Hello, I'm Yosuke from RIT Tokyo. Today, I would like to introduce To the Power. Before getting started, allow me to introduce our group. Rakuten has a huge amount of unstructured data which has been increasing day by day. We are providing distributed storage system, distributed file system, data stream processing, and image search. Our presentation are going to focus on how our technology are helping Rakuten. Our domain provides for software, Roma as key value store, LeoFS distributed file system, stream processing, and image search. Also, Roma is used with 13 services in Rakuten, and LeoFS is used with 8 services, but in this year, more growing LeoFS users. Today we are going to share 2 topics. First part is LeoFS. Other part is stream processing from user Canada. Let's move my presentation. Today's title is Open the New Door. LeoFS is working on new version, which is version 1.0, which is share latter part. I have been seeking the best distributed file system for the web for more than 3 years. So we released LeoFS as open source software on July of last year on GitHub, and which is released a new version yesterday. The version number is 0.6.0. Now LeoFS developer is 3 Japanese developer and French engineer. Our company has LeoFS support team from last year. Also in this year, LeoFS will cover about 60% of media files in our Rakuten. So in this March, I made a presentation at Alan User Conference 2013 in San Francisco. I aim to spread LeoFS users outside Rakuten. We are still sharing and promoting LeoFS all over the world outside Rakuten. So thanks to that, LeoFS users are gradually increasing, such as China, Russia, Europe, and US. First topic, motivation. As of 2010, I found storage problems, so we need to get away from using expensive hardware-based storage to something. So first, because they have some problems. First is high costs, initial costs and running costs is very high. Second is possibility of single point failure. Third, not easily scale. Storage expansion is difficult during period of increasing data. So we need to develop elastic storage system at low cost. I'm focusing on 3 important things. First one is high availability. LeoFS is always available. Second is high cost performance ratio. Good performance and using minimum resources. Third is high scalability. LeoFS already cover small size to large file size. And photo, movie, unstructured data already covered it. Second topic is overview. Here is the example of LeoFS architecture, system architecture. It's very simple. LeoFS consists of three functions: LeoFS gateway, storage, and manager. Data flow is application to load balancer to gateway to storage, not through LeoFS manager. LeoFS manager monitored LeoFS gateway and storage in order to keep running a LeoFS system. Also, LeoFS has built-in support SNLP agent, so you are easily monitor LeoFS with monitoring system such as Nagios and Zabbix. Next is gateway. Gateway consists of stateless proxy and object cache. You can easily increase gateway nodes during periods of high load situation. A gateway handles HTTP request and response. You are able to use REST API and S3 or S3 API. I consider links to support Swift API to realize to OpenStack integration. Also, it is already built-in object cache mechanism in gateway. Thanks to that, it is able to realize low latency, good performance, and restrain network traffic between gateway and storage. Next is storage. A storage cluster consists of many storage nodes. It using peer-to-peer network. You are able to see it as a huge capacity storage, which loosely connect between storage nodes. And storage handle get, put, and delete, as well as metadata. Storage consists of object store mechanism and metadata storage process. A storage consists of, as I mentioned, storage consists of AE workers, and storage engine consists of metadata and object container. Object container manage log structure file, and metadata keeps an in-memory index of all data. And storage engine has replicator and repairer with queue mechanism in order to keep consistency object. Here is case of retrieving an object from the storage. This method is very simple. First, storage engine retrieve a metadata, left side, metadata storage. Then retrieve an object from the object container when using file size and file offset. This case is retrieving an object from the storage. First, storage engine insert a metadata into the metadata storage. Then append an object container object into the object container. But this mechanism is side effects. Storage engine sometimes need to remove unnecessary files as well as metadata. LeoFS has been taking a measure for less than effect and compaction. It has suspend compaction and resume compaction. Here is LeoFS data structure diagram. It has 3 layers: metadata, middle, and object container. Metadata consists of files, file name, file size, checksum, and so on. needle is object. It consists of metadata, gray, color is gray, and key, and user metadata, and actual file. So object tag container consists of any needles. It managed unstructured file. LeoFS already support a large object support because realized to equalize disk usage of every storage nodes and to realize high I/O efficiency and high availability. This case is write operation. An object is divided to plural objects in gateway, which is stored storage nodes. A size of chunk size is 5 megabytes. The chunk object is replicated into the storage cluster as well as metadata. Next is manager. Manager always monitor storage nodes and gateway nodes in order to keep running LeoFS and provide easy operation mechanism to gateway and storage cluster. You can easily operate LeoFS with manager. For example, node status, retrieving node status, suspend storage node, resume, detach, and so on. Today I'm going to share two new features. First one is Insight as LeoFS QoS, and second is multi-data center replication. From last month, we have been developing LeoFS QoS, which is called Leo Insight. I'm planning to include it with version 1.0. It realizes two things. First, it is able to control requests from client to LeoFS gateway on 1 minute. Then it refuses requests from one of client when over defined number of requests. Second, it is able to manage and see LeoFS traffic data for administrators with Leo Center and GUI console. So it is LeoFS Defender. This is manager message flow from LeoFS gateway to Leo Insight. Leo Insight uses distributed queue system as LDB and time series DB which is named called Savannah. So over defined the threshold. Leo Insight notifier message to Leo Gateway. So Leo Gateway received a message. So Leo Gateway refused one of user's requests. So because LeoFS need to keep high performance. Next is more scalability and more availability. So unstructured data has been exponentially increasing day by day in our company. So we need to realize high scalability, high availability storage system, and easy operation for administrator it's necessary. So also I consider how to realize much data center replication more simply. No simple room failure and no performance degradation. They are most important things. In this slide, I'm going to share the case of 3 regions and 5 replicas. It needs 3 configurations in order to realize multi-data center replication. First one is the method of replication, which has async replication and synchronous replication. Second is number of replication target DCs. Third is number of replica DC. One DC is copied up to defined number of replicas. You need to only set 3 configurations to every DC. The sample is 1, 2, 3. Also, every configuration is monitored and replicated every DCs. Next, I'm going to share the write operation. At first, you need to create a bucket and set and decide use region DC1 or DC2 or DC3. Then an object is replicated to local DC and remote DC, DC2 or DC3 that adhere to the configuration. This example uses synchronous replication. If you need hard consistency, you are able to select this way. A storage decides a primary node from the link routing table. The primary node is in charge of reader. Other nodes is follower. The primary node is responsible to replicate an object to local region 2 and then replicated remote region DC2 and DC3 and check consistency, object consistency of the and when it found missing replication and or inconsistency object, it will eventually resolve this problem. This slide is geographical optimization, which uses geographic table, right side, top or right side. I did not share for much DC replica placement. It is has more specification. So I'll publish its detail on the LeoFS blog. Next is Center. LeoFS Center is web-based administrative console for inspecting and manipulating LeoFS storage cluster and LeoFS gateway. So it has administrator tools and access log analysis. Access log analysis is using Elasticsearch, and Elasticsearch is Kibana. This slide is access log analysis image. But this function is still better. I'm planning to increase this function. Last part is brief benchmark report. About 3 weeks ago, we took benchmark about LeoFS in 14 giga Ethernet network. Our environment is like this. Number of gateway nodes is 1. Number of storage nodes is 4. Consistency level, number of replicas is 3. Network is 14 gigabytes. So this result is has reached 5,200 operation per second. In other words, 5 gigabps. Latency 99 percentile, and mean and median is here. File size, average file size is 128 kilobyte. Read and write 80% and 20%. Duration time is 20 minutes. Also, this slide is average file size 1 megabyte. Other condition is same. This result has reached 500 operation per second and 5 gigabps. Same result. Also, this result is from one of LeoFS users. This result is file average is 1 megabyte. Condition is same before same. This result has reached 1,800 operation per sec. Also 1.8 gigabytes and 14.4 gigabps. Very good result. This condition is 14 gigabyte 10 giga network, 8 core servers. Number of storage is 6. Number of gateway is 3. Benchmark node is 2. I have been developing LeoFS and increasing LeoFS day by day. So I'm working on LeoFS version 1.0, which will be released at around at the end of next month. This slide is LeoFS milestones. Current status is here. Next version is 1.0. Will realize multi-data center replication and LeoFS QoS. And 1.2, we will realize OpenStack integration and more. That's it from me. And if you want LeoFS sticker, let me know. Please let me know. Thank you very much. If you have any question.
So you mentioned there are some users using LeoFS other than Rakuten. Is there any companies that we would know about using this file storage system? That you can share?
In Japan, unfortunately, users very few, but in China has been gradually increasing. A few days ago, Taobao engineer mentioned LeoFS, and Europe our developers is three, two Japanese and one French engineer. So he's spreading LeoFS Europe. So thanks to that, LeoFS well known Europe and Russia, but US same situation in Japan.
Can I think LeoFS is another way of virtualization database, right? Storage virtualization, right? So right now you have support the Amazon S3, right? Can I have a question? When you trying to support the Google Drive?
Google Drive.
Yeah, because now we all using Google Drive because they support the CDS CDN systems itself. So it's very useful for us if we can use Google Drive for that one.
I see. So I mentioned, as I mentioned, LeoFS milestones here. So next phase, I going to gather any information next to LeoFS. Growing next to grow next to LeoFS. So currently LeoFS support S3 API and REST API. So next version will support Swift API. So in the future, another will support API and platform.
Futures mean next year.
Next year.
Thank you.
Thank you.
Sorry. Do you think most appealing point for that LeoFS for Chinese people and Russian people? Do you think?
As I mentioned, this slide is one of LeoFS users. Last year, I received this result from German users. So he mentioned about LeoFS. He said LeoFS its performance very good and high availability, but as I mentioned, data center multi-replication. So I'm focusing on high scalability, availability, high cost performance ratio is clear, I think. So next point is high scalability.
Thank you.
I have checked out source code of LeoFS, and LeoFS is basically written in Erlang, right? But in the source code, I see a lot of C language source code.
Source code C and Erlang.
Yeah. So I want to ask, what part in LeoFS is used or is written in C, and which part is
another language. At the beginning, develop LeoFS. I at that time I use Java and C++, but very huge codes become a very huge code. So I surveyed other language such as Erlang and Scala, and so on. But Alan is very specific network server, developing network server. So, for example, React and MochiWeb, RakutenMQ made by Alan. So I decided to use Alan. So Alan is a special networks, developed network program.
And C language is used for which part in the
Cache mechanism, only cache mechanism.
Recently, I used LeoFS with my application.
Oh, thank you.
I used S3 SDK for request to LeoFS, and I met pass error with return of LeoFS. So I want to know about how compatibility of LeoFS and this is SSP.
Compatibility. We have documentation, and in documentation include S3 API compatibility, table of S3 API compatibility. Here is a table of S3 compatibility. Could you see it? What function is failed?
I used set user metadata.
Does not yet. Support does not yet. Sorry.
Is it will be supported?
Yes, in the future. Okay, thank you. Next part is user Kaneta present string processing.
Okay, I'm Yusa Kaneta from Rakuten Institute of Technology. Today, I would like to talk about counting big data by streaming algorithms and introduce its use in Rakuten. I guess from streaming processing, some of you expect a talk on Stone or something like that, but today's talk is on algorithms. Okay, first of all, let me introduce myself. My name is Yusak Kaneta, and I joined Rakuten in April last year after earning my PhD, and currently work at Rakuten Institute of Technology, RIT. My research interests include these topics. The first is string processing, especially pattern matching algorithms. The second is hardware design using FPGA. Do you know FPGA? FPGA is really fun. And finally, we can write circuit in program. This is amazing. Yeah. And finally, we really like bitwise tricks and techniques. Actually, I have written some papers on the topic. If you also love these tricks and techniques, I strongly recommend it that you read the chapter 7 of the Art of Computer Programming and Hackers Delight. Please buy them in Rakuten. Okay, let's get to the main part of this talk. First, I would like to give you the background of this talk. Counting is a fundamental operation in data analysis. For example, if we want to know some averages or to describe some histogram, we need counting information. Counting small data is quite easy, but counting big data can be difficult because it needs a huge amount of memory that does not fit into recent main memory. As you know, batch processing, like Hadoop, is a possible solution to this problem. But there are two issues. Basically, batch processing like Hadoop has a high latency, and it also requires a cluster of machine. This is high cost. So these are our goals. The first is we want to reduce memory for cost reduction. The second is we want to reduce latency for quick business decision. And finally, we want to achieve high accuracy for correct business decision. This means I can relax the problem and allow for some approximation. As for to fulfill all of these goals, we employ another approach called streaming algorithms. Streaming algorithms is a type of algorithms and getting more and more important and common in web companies. For example, if you read the paper on Google Power Drill project or the code of Twitter's algebra, you can find some streaming algorithms. The key feature of streaming algorithms is this. The first feature is streaming algorithms run on limited memory. The second key feature is streaming algorithms has a low latency. And finally, streaming algorithms has a theoretical guarantee for accuracy. This feature is very, very important for us. So to make a streaming algorithm available for all of engineers in Rakuten, we internally provide a C library for streaming algorithms called LibSketch. LibSketch has three main advantages of being memory efficient, achieving high speed, and keeping high accuracy. We also provide some bindings for Python and Ruby. Let me explain why we chose C as our language. The main target of the library is Python and Ruby users, because in Rakuten, Python is popular with data scientists, and this is just in my opinion, but Ruby can be a great option for stream processing in combination with FluentD. FluentD allow us to make streaming algorithms distributed easily. This is the main reason why we wrote our library in C. Okay, next I will introduce a use of streaming algorithms in Rakuten. Rakuten has a variety types of data, and we want to know, for example, how many unique users are checking a specific item in a day. Or we want to know how many products sold in a day. For these queries, we can use streaming algorithms like hyperloglog or count-min-sketch. Today, I would like to focus on the first type of queries and hyperloglog algorithm. The first type of query is the unique item count problem. So as a naive approach, for example, we can use the dictionary type in Python like this. But this approach can require a large amount of memory depending on the answers. On the other hand, we can also use a streaming algorithm called hyperloglog. Hyperloglog can count unique items approximately in a very, very small space, and hyperloglog requires just a fixed amount of memory. This is a very, very great feature because we can estimate the usage of the resource usage. I would like to note that Google recently proposed an improved version of hyperloglog algorithm called hyperloglog++. So hyperloglog continues to evolve. The basic idea of hyperloglog is hash function, harmonic mean, and stochastic averaging. Okay, due to time constraint, we will omit the detail, but hyperloglog algorithm is quite simple and easy to implement. Okay, let's see a demo. Can you see? The left is the execution of a naive approach based on Ruby's set type. This naive approach can compute the exact value. This is great, but slightly small. On the other hand, streaming algorithm is very, very fast, but it computes some approximation. Okay. Finally, I would like to show a performance evaluation result. I counted the number of unique items in item set stored in Rakuten. Compared to the naive approach, streaming algorithm can achieve very, very good result. For example, streaming algorithm can reduce 99% memory and achieve 4 times speed up and keeping almost 100% accuracy. Yeah, of course, this experiment it was run over a small data set, but we are using hyperloglog algorithm for much bigger data. Okay, as conclusion, today I introduced use case of streaming algorithms in Rakuten. We are using streaming algorithms for mainly data analysis tasks. We have an internal C library called libsketch and also provide bindings for Ruby and Python. In the future, we would like to implement other algorithms for more complex data analysis. Okay, that's all. Thank you for your listening.
Thank you very much. You have good presentation. We will have a Q&A session. Please raise your hand if you have any questions.
Do the streaming algorithms do incremental updates?
Update?
Yes.
Yes.
They naturally handle it.
Yeah, stream algorithm basically scan the input data sequentially, so we can support.
Does that imply they only go through the data once?
Mm-hmm. Sorry?
Do they go through the data from start to finish once?
Yeah.
If it's on a tape, or does it go back and forth?
At any time, we can query the result. So we start to reading the start to end. If we want to the result at some point, we can query and return the result.
Okay, thank you.
Thank you.
Are there any other questions?
Yeah, correct me if I'm wrong. You talk about algorithm, but I don't see any algorithm there. Okay, so is a hyperloglog algorithm supporting the chain? For example, you counting from the first day until the 10th day, but suddenly you found in the second day it does work wrong. and you want to change the second day, is it supporting the change in supporting, or you have to throw everything and count from the beginning?
Yeah, basically, we can count the all range, but recently I tried to, yeah, for each day.
Okay, so if some part of the data is wrong and you're counting it, and you have to count from the beginning, right?
Yeah, I think your question is very, very important. We want to know, and yeah, I try to work. Yeah, please come next year.
It depends some randomized algorithm, right?
Mm-hmm. Random. Yeah, we can. Yeah.
I think the randomized algorithm is very important to streaming algorithms. How do you make sure that your randomized algorithm are okay with the big data wrapping?
Yeah, I have no answer to the question, so let's discuss after this session.
Okay.
Thank you. Some of you may have more questions, but I'm afraid that we have to stop here because we are running out of time. So we'll end this session. And thank you very much, Mr. Hara and Dr. Kaneta.